There are many different models of this basic rich get richer phenomenon. What I'll do in this video is describe a particularly simple model that will give you the general idea and flavor of these models. More realistic models are usually variations off of this one. The model I'll present is described more fully elsewhere. One good resource is the book by Easley and Kleinberg. I'll be sure to put the reference here. My discussion follows theirs pretty closely. The paper by Mitzenmacher on a history of generative models of power laws also has a nice discussion of this. Okay, so here's the idea. So this is a model of what's called preferential attachment for how we might think a network would grow. So I'm going to describe this, for the sake of concreteness, to picture the World Wide Web growing site by site, a very simple model for that. And in the next video, I'll talk about how this is a more general model. So here's the picture. Let's imagine we're growing a network, and at this particular point in this growth process, we have 1, 2, 3, 4, 5, 6. So these circles are pages, and then these arrows indicate a link. So that would say that this page links to this one, this page links to this one, and so on. This page to this one to that one. So this is a very simple model of a little part of the World Wide Web. So in this model, we would grow the network, the web, one page at a time. So we've already started this process. Here's the rule for determining what the next node will be. So, or sorry, what the next site will be. So in other words, I'm going to choose a new page, put a new page here, and it's going to make a link to one of the existing pages. So new page will link to one existing page. So obviously not realistic. Make a new page, you're probably going to make more than one link. But again, this is just a simple model to give a flavor of how this works. All right, so what am I going to do? So with probability P, I'm going to just choose to link to a page at random. Sorry about that. The phone rang. Turned out to be a wrong number. All right, so with probability P, I'm going to link to a page at random. So maybe the picture here is this is just a portion of a web, and all of these are pages about power laws. And I'm making a new page about complex systems, and I want to mention power laws, and I just need a link to any old power law page, so I just choose one at random. So there's some chance that maybe that's how I would choose the link for this new page. But there's another way to do it. So with probability 1 minus P, I'm going to link to a page with probability proportional Okay, so with probability P, I link to a page at random. With probability 1 minus P, I do something else. Now I'm going to link to a page not at random, but with a probability proportional to the page's current number of in-links. So what do I mean by in-links? So this page has no in-links. Nothing links to it. this and this and this page all have 0 in links. Let's see, maybe I'll indicate these with orange numbers. 0, 0, 0, 0. This page has 1 in link because one page, this guy, links into that one. And this page, 1, 2, 3, 4, has 4 in links. So again, here's the picture. I'm going to add I'm adding a new page and I'm going to link someplace. So how am I going to do that? So with probability p, so maybe p is 0.1. So 10% of the time I just link to a page at random. Then I would go to each of these with an equal probability. There are 1, 2, 3, 4, 5, 6 choices. So I'll go to this with probability a sixth, this with a probability 1 over 6, and so on. With probability 1 minus p, 90% of the time, I'm instead of operating at random, I'm going to choose more likely than not the page with more links. So this has a weight or number of in-links of 4. This has a number of in-links of 5. So I would choose this page 4/5 of the time with a probability 4 over 5, and this with a probability of 1 over 5. Again, the 5 comes from normalizing. There's 5, total of 5 in-links. So if I end up choosing this way to do it, way 1, way 2, if I choose this way to do it, I'm more likely than not going to go to a page that's already pretty popular. So this is the idea of preferential attachment. I'm going to choose to attach to the page that already has a lot attached to it. Why might I do that? Well, if I'm going to link to a power law page, I want to link to not just any old power law page. I want to link to a good power law page. But I don't know that much about power laws, perhaps. So what would I take as a proxy, as a stand-in for how good a page was? Well, just how popular it was. Maybe I want to read a book, a novel or something, and I don't know what novel I want to read. Well, but I want to read a good novel, but I don't know how to discern if a novel's good, so I'll just discern if a novel's popular. Then I'll have read that novel, and it will become more popular still, and so on and so on. So this is a simple model of preferential attachment. With some probability, we attach more often to those pages that are already more popular. So what happens as the network grows? Well, we would expect, as long as we do this proportional linking sometimes, that these pages, just as the network is created, there are a few pages which, just by random chance, happen to become a little bit more popular, that their popularity is going to tend to run away. So we'd expect lots of not so popular pages, and then a smaller amount of very, very popular pages. So what would that distribution look like? Well, you'll probably not be shocked to learn that this tends towards a power law. So the fraction of pages with k in links is proportional to power law of this form, and alpha is 1 plus 1 over 1 minus p. So this particular result is not at all obvious. It takes quite a bit of math to get here. The simplest way that I know to show this is to take this discrete process, approximate it with a continuous process, write the dynamics down in terms of a differential equation, and solve the differential equation. And both Easley and Kleinberg and Mitzenmacher go through that derivation. It's possible to do more rigorously and carefully without making the differential equation approximation, but that requires a good bit more mathematics. So again, this result should not be obvious. Maybe it's not shocking that there's a power law, but that it's this particular exponent is not intended to be an obvious statement. That takes a bit of work to derive. However, once we have this, we can use this to sort of check to see that this makes sense. So what I mean by this is as follows. So let's imagine graphing alpha as a function of p. So there's alpha, there's p, be 0 up to 1. So because remember, p is a probability, so it's got to be between 0 and 1. Now if p is 0, this becomes 1 plus 1 over 1, and that's 2. And as p increases, 1 minus p decreases, so the thing downstairs is getting smaller, this gets larger. And as we approach 1, we have 1 minus 1, that's 1 over 0, that diverges. So this is going to look something very roughly like this. All right, so I claim that this sort of makes sense. Let me justify this claim. So what's p? So p is the probability that you link to a page at random. So if p is large, we're not doing much preferential linking, and we would expect a very fast decaying power law if we get one at all. And that's what this says. The larger the exponent alpha, the faster the decay is for the power law. On the other hand, if we have a p of 0, that means we're always doing preferential. That's sort of the longest tail that we can get, where the sort of this winner-take-all dynamics is the most strongly pronounced. That would mean we would have a power law that decays slowly, and that's what we see. We see a smaller exponent, an exponent of 2 instead of something much larger. So the bottom line is, sort of to recap, this is just about the simplest model of preferential attachment, obviously an oversimplification, but still I think it captures the essence of this idea that we have some likelihood to attach to or read or recommend or link or go to those things which are already more popular. And if you carry that mathematics out, sure enough, you do indeed get a power law. A power law behaves like this, which makes sense in the context of the original model. So this is one mechanism for generating power laws. Preferential attachment, like I've just described, of models of the sort I've just described, tend to give power laws.